Hello viewers, in this video I will discuss about continuous charge distributions. Before talking about continuous charge distributions, we will discuss something which we have discussed in earlier lectures, that is electric field due to a point charge. Okay, so in previous lectures we have discussed about electric field due to a point charge. Okay, so from Coulomb's law we know that the electric field is given by F by Q. Okay, so that is if we have a charge arrangement like this. Okay, so the electric field due to this charge and the electric field experienced by this charge is given by E is equal to F by Q. So from Coulomb's law we know that the value of force is nothing but 1 by 4 pi epsilon naught Q by R square, the distance. Okay, so now what could be the value of electric field? So here the value of electric field is, so when you divide this force by Q, we'll be getting the value of electric field as 1 by 4 pi epsilon naught Q by R square. So this is the value of electric field for a point charge. Okay, so now we have also discussed about the net electric field due to a system of charges. So when we have charges like this Q1, Q2, Q3 and Q4, when let's take a point O. So the net electric field due to all these charges at this point. So this arrangement we call it as system of charges. Okay, so according to the principle of superposition, the net electric field at this point O is nothing but the algebraic sum or the vector sum of the electric field due to all individual charges. Okay, this we have discussed in the previous lectures itself. Okay, so this arrangement of charges, this system of charges, we call it as this system of charges we call it as discrete system of charges. We call it as discrete system of charges. So what is discrete? Here we see that discrete means charges are of different. So see that each charges they have different. Okay, they have different magnitudes. They are different in nature. Then the charges are of a different and they has its own existence. Okay, so here we see that each charge has its own existence. Okay, so this arrangement we call it as discrete system of charges. So see that each charges are different and they has its own existence. So this arrangement we call it as discrete system of charges. In case of discrete system of charges, finding the net electric field is very easy. Nothing but it is the algebraic sum. Okay, so the net electric field is nothing but the algebraic sum of all electric fields. All electric fields due to this all charges of electric fields due to the all individual charges. Okay, so here there is no need of any calculus. See here, so here there is no need of calculus. So no need of calculus to find the net electric field. Just we are just adding up all the vector sum of all charges. Okay, so this is about the discrete system of charges. So now we'll move on to the topic continuous charge distributions. So we'll see what is the difference between this discrete and the continuous charge distributions. So this is about discrete. Now we will see about continuous charge distributions. So which are called continuous charge distributions? See, charges are uniformly distributed over the conductor. So in case of continuous charge distributions, here we can see that the charges are uniformly distributed over the conductor. And one more point is infinite number of charges. So infinite number of charges, so closely arranged. See that they are closely arranged with minor space between them. So this is about continuous charge distribution. Okay, see here, they are uniformly distributed over the conductor and a infinite number, many charges, they are very closely arranged with very small minor space between them. Okay, so we have three types of continuous charge distributions. Okay, so three types of this distribution. Okay, so now we'll see what are the three types. We have first one, linear charge distribution. Then we have second one, surface charge distribution. And in third we have volume charge distribution. So these are the three kinds of continuous charge distribution. So we will see each in detail. Okay, we will see the each in detail. We will see each. So we will see individually what is linear, what is surface, and what is volume charge distribution, and we'll see. Okay, fine. So first one, you are going to see about a linear charge distribution. So which arrangement we call it as linear charge distribution? See that the charges here, only for this case, charges are non-uniformly. See, the charges are non-uniformly distributed over the length of the conductor. See, over the length of the conductor. So distributed over only the length of the conductor. Okay, so let us see an arrangement like this. Okay, so we see that charges are non-uniformly distributed over the length of, let us consider a line arrangement of charges. Okay, so if you want to find the arrangement of charge at this particular point P, which is at a capital distance r. Okay, so we need to find the electric field at this point P due to this arrangement of charges. See that the total length is given as L. Okay, fine. So here I am going to introduce a term, we'll call it as linear charge density, which we call it as lambda. This we call it as lambda. Okay, so this we call it as lambda is nothing but charge per unit length. Call as lambda as the charge per unit length, and the unit of this is coulomb per meter. Okay, so this lambda is written as charge, nothing but Q by unit length. Let's take it as L. Okay, so why we have introduced this term lambda? Okay, so here we see that this arrangement, I will show you an example. So let us consider this as a line arrangement of charges, a wire. Okay, so see the length of this wire, it is very small. It is very easy to find the total length of this wire. Okay, so keep this in mind. Now see the length of this wire, it is very long. Okay, even this also could be easily calculated, but in most practical cases we see that the length of the conductor will be very long. In such cases it is very difficult to find the length of the conductor. In such cases, how to find the value of charge? So the value of charge is found by charge per unit length. Okay, so for example, in this case, let us consider the unit length as 1 meter. So the value of charge could be found by, for 1 meter, what is the value of charge? For 1 meter, what is the value of charge? For 1 meter, what is the value of charge? Okay, so depending upon, for finding the value for up to 1 meter, it is very easy to find the value of the charge for total length of the conductor. So for that cases, we have introduced this term lambda, which specifies the charge per unit length. Okay. So if we found the value of charge for one particular length, it is easy to find the total length of the charges. Okay. So lambda is nothing but Q by L. So here to find the, see in this case, to find the total electric field, I am going to take a small charge element. Okay. A small charge element. Why you are taking this small charge element? Because you know that electric field due to a point charge. See, due to a point charge, we have a formula. K is equal to K Q by R square. K or 1 by 4 pi epsilon, whatever may be, both are equal. K Q by R square. This formula is applied only for a point charge. But here we have an arrangement like this. Okay, so this formula could not be directly used for this kind of arrangement. Okay, so for that cases, so I'm going to take a very small element as similar to a point charge. Okay, so let us take the length of this charge as dl, and the charge of this particular small element, let us take it as dq, and what will be the value of electric field here? This is nothing but dE. Okay, so here I'm taking as dE. So now we can use this formula directly here. Okay, you know the E is equal to kq by r square. So here by finding the value of dE, then after finding the value of dE, when you integrate it with up to this limit, when you integrate with this limit, we could easily find the net electric field due to this charges at this point P. Okay, so now let us see. So you know that dE is nothing but, so substitute K. So here the value of charge here is dQ, distance here is nothing but r square. Okay, K dQ by r square. So now here if you know that the value of lambda is Q by L for the total element. What is the value of lambda for this particular element? For this particular element, the value of lambda is nothing but dQ by, what is the length? dL. So lambda is equal to dQ by dL. So instead of dQ, I am going to replace it by lambda dL. So it is nothing but K lambda dL by r square. So the value of d is K lambda dL by r square. Okay. So after finding d, to find the total electric field, the net electric field is found by integrating dE. So I am going to integrate K lambda dL by r square. So you can take K lambda as constant by r square as constant. So I am going to integrate dL up to limit 0 to L. So here we have 0 to L. So this is the general value of representing. This is the general value of representing. So this is L. The net electric field due to line charge distribution or linear charge distribution. Okay, so this is the way of finding the net electric field due to linear charge distribution. So it is a continuous charge arrangement. Okay, so now we will see the next one, surface charge distribution. Okay. So second one we have surface charge distribution. So here the charges are, in this case we can write the charges are uniformly distributed over the, not the length, over the surface of the conductor. So in this case we see that the charges are uniformly distributed over the surface of a conductor. Okay, so now let us take an arrangement like this. Okay, so we have charges are uniformly distributed. So when we consider a point P at the distance R, what will be the net electric field due to this surface charge arrangement? Okay, so here also I am going to, as we see lambda in case of linear charge distribution, see. Now let us consider a surface like this. So a surface, a plane, it does not have any thickness. Okay, so it is very easy for you to find the surface. Okay, but in most practical cases we see that if the area is very large, so in such cases it is preferable to find the term. So here I am going to introduce the term which we call it as surface charge density. So as we discussed linear charge density for linear charge distribution, so here also I am going to introduce surface charge density. It is given by term called as sigma. We call it as sigma. So what is sigma? Is nothing but charge per unit area. This is charge per unit area. So the unit is nothing but coulomb per meter square. It is coulomb per meter square. Okay, so as we discussed, charge lambda as charge per unit length. So for unit area, what is the value of charge? You could easily find. Then we could easily find the total value of charge for the whole area of the conductor. Okay, so what is the value of sigma here? It is nothing but it is Q by A for the overall. For overall, the sigma is equal to Q by A. Okay, so here we also consider a small element. Okay, like a small big piece of a cake from a very large piece of cake. Imagine. Okay, so we considering a very small element. Okay, so here I am considering this very small element as dA. Okay, as dA, and the charge of this particular element, let us take it as dq. Okay, the electric field dE. Okay, so this is the notation. Okay, so now what is the value of sigma for this particular arrangement? So sigma is nothing but here it is dq by dA. This is the value of sigma for this kind of arrangement. So what is the value of electric field? You know, it is dq, it is nothing but k. So here the charge, it is nothing but dq by distance is r square. So k, instead of dq, we can replace it by sigma dA by r square. Okay, this is dE. So after finding dE, now to find the net electric field, I have to integrate dE. Okay, so integration of dA by r square. So k sigma by r square, integration of dA with respect to 0 to a. This is the net electric field. So this is the net electric field with in case of your surface charge distribution. Okay, so this is the general way of representation of your surface charge distribution. Okay. Okay, next we will see about the volume charge distribution. Okay. So next we have volume charge distribution. So that is the third one. We have volume charge distribution. So here also the charges are uniformly distributed over the volume of the conductor. Okay, so here we are going to introduce a term which we call it as volume charge density. So volume charge density. So here the volume charge density is given by the symbol rho. We call it as rho. RHO, rho. So here what is rho? Charge per unit volume. Charge per unit volume. Here it is coulomb per meter cube. Okay. So similarly, you know, volume means let us consider a cube arrangement. So we have a cube arrangement. So what could be the value of electric field at a point P from this particular cube arrangement, which is at a place at distance r? Okay, so you know, here the value of rho will be, generally it is nothing but Q by V for volume. Okay, so here also let us consider a small piece of element, very small piece of element like this, very small. Okay, so you know the value of charge here is, let us take it as dq, and here the small element is dV with respect to volume, and the electric field is also dE. So we have to find the value of this electric field. Okay, so for this particular small charge arrangement, the rho could be written as dq by dV. Okay, so what is dV? K dq by r square. So here I am replacing, so k rho dV by r square. So net electric field is nothing but you are integrating, so integration with nothing but k rho dV by r square, which is k rho by r square. I am integrating the value of dV for respect to 0 to V. This is the net representation, net value of electric field due to volume charge distribution. Okay, so this is about volume charge distribution. Okay, Fine. So we will see some examples with respect to linear charge distribution. So here I will discuss about two examples. We discuss about the linear charge distribution arrangement. Okay. So we will see some examples. Okay. So I have an arrangement like this. So here it explains about a linear charge distribution. Okay. Okay. We have a conductor like this. See, I have a point P here, which is placed at a distance x from the conductor. Okay, so the total length of the conductor, let us take it as L. Let us take it as capital L. Okay, so now I want to find the total net electric field at this particular point P. So now here we have to know what is the direction of the electric field of each particular point charges. So you know that for a point charge Q, the direction of electric field here would be like this. It will be for a positive charge, it is radially in outward direction. This could be the direction of the electric field for each point charge. So let us apply here also. For each point charge is placed here, that will be, see, I am applying here. So that could be the direction of the electric field. So when you see for all the charges, we see that mostly in this direction, this particular direction of electric field will pass through this point P. Okay, so mostly this directions. So the electric field is directed towards this direction for this particular point P by considering this arrangement. Okay, so now we will see what could be the net electric field at this particular point P for this particular arrangement. Okay, so for this we are going to consider a very small element here, a very small element. Now here I am considering that element as dr. Okay, element as dr, which is placed at a distance of r from the point P. So the distance is r. Let us take it as r. Okay. So here also I'm going to introduce a term, what lambda, linear charge q by L. So if I have the value of lambda for this particular small element, so the charge for this particular small element is nothing but dq, and the electric field is also dE. So here the charge arrangement is dq, so the length is nothing but dr. Okay, so this is the arrangement. Okay, so now we have to find the electric field dE. First we will find what is dE. So dE is known as k dq by the distance as r square. Okay, so here k dq replaced by lambda dr by r square. So it is okay, fine. So this is the value of the electric field dE. So to find the net electric field, this is the point P. So this point P is placed at distance x from one end of the conductor, and it is placed at distance of x plus L to another end of the conductor. So that is the limit. From this point P, x is one of the limit and x plus L is the another limit. Okay, so now I'm going to apply. So to find the net electric field, I'm going to integrate this dE for the specified limits. Okay, so integration of k lambda d lambda by r square, sorry, k lambda dr, sorry, by r square. Okay, so k lambda, so this is dr by r square. So the limits are x and x plus L, x and x plus L. We will see what happens. Okay, so here we have will be equal to k lambda. So when you do the integration, you will be getting the value as minus 1 by r, and the limits are x and x plus L, which will be equal to k lambda minus of 1 by, so for r it is nothing but x plus L. So minus and minus will become plus by 1 by x. So here the net electric field will be equal to k lambda 1 by x minus of 1 by x plus L. Okay, so this is the net electric field for this particular arrangement of linear charges. Okay, so for this kind of arrangement, so we have found, if you know the value of x, L and lambda, so lambda k they will be constant terms. Okay, if you know all these terms, it will be easy to find the net electric field at this point P. Okay, Fine. So now we'll see another one example. We will see another one example. Okay, here also I'm going to see another linear charge distribution arrangement. Oh, I'm taking a very long conductor. Plus, 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 plus. Okay. So I have taken a very long conductor and I am going to find the net electric field at a point P here. At a point P here. Okay. So as you know, again I'll draw the direction of the electric field for a positive charge. See, this is the will be radially outward directions for a positive charge. Okay. So let us apply here also. See, let us apply to the end points. So here I am applying this. See here, this will be the direction of the electric field. Okay, something radially outward direction. See, this particular arrangement, it sees the point P. So this particular, okay, so here we can say, so this particular point reaches this point P. Okay, let us set, this is the limit. After this, we see that no electric field reaches this point P. Okay. Similarly, we have for all the charges, this will be, this arrangement will, this direction of electric field reaches point P. This direction of electric field reaches point P. This one, this one, this one. So from this, it will be straight. Similarly, as upwards also, we can see that this arrangement will reach this point P. Okay, sorry. This direction will reaches this point P. Similarly, this also reaches this point P. From this also reaches this point P. Here also reaches this point P. Okay. So, like this. Okay. So, this will be the direction of the electric field with respect to this point P. Okay. Okay. So, now we will find the net electric field with respect to the upper and lower limits. Okay. So, we will consider only the limits. We will consider only the limits. It's very difficult to rub all this. Okay, I think I rubbed it properly. Okay, fine. Okay, so now let us consider this is the limits which touches this point P. Let us take this as angle theta 2 and this as angle theta 1. Okay, so as usual, to find net electric field, we will consider a very small element here. Very small element. Let us take this as, oh, this total length, let us take it as L, capital L. First of all, I think I forgot it. Okay, so this particular element, let us take it as dl, and which is placed at distance small l. This is capital L, this is small dl, and this is small l. Okay, so this is placed. Okay, so this is at a point, it is at a distance of r from this point P. So see here, it is at a distance r from the point P, and see the angle made by this particular arrangement is phi. The angle made by this particular dl with respect to point P in this axis is nothing but phi. Okay, this phi varies from theta 1 to theta 2. Okay, so with respect representing the equation in terms of phi and applying this limits theta 1 theta 2, we could easily find the value of the net electric field. Okay, so this is the arrangement we have done. So you know that the charge of this particular small element, let's take it as dq, the electric field of this particular element as dE, and now we see that this dE will be pointing in this direction. So this is the dE. Okay, so for this dE we have two components. See, okay, if this is phi, this is also phi. So here this dE we have two components. This point, we have two components. One is dE cos phi, because along the angle it is, and this is dE sin phi. Okay, this is d sine phi, d cos phi. So we have to find individually so this component, if we call it as E net in, we can call it as, oh, sorry, perpendicular component. So this is call it as perpendicular component of electric field. This we call it as parallel component of electric field. Okay, so first will find the expression for DE, then we will find the limits of the parallel and perpendicular conditions. Okay, fine. So first DE, you know that DE is nothing but K dq by r square. So K dq by r square. Okay, so here you know that from lambda, you know that. So lambda is nothing but dq by dl. So now I am going to replace this by dq by dl. So which is equal to K lambda dl by r square. Okay, so I have said already you have to represent the equation with respect to phi. Okay, so that will be very easy for me to find the answer with respect to the limits theta 1 and theta 2. So all the expressions should be in terms of phi. So what I am going to do is, this I forgot to mention the distance, this as x. Okay, from this to the point P. Let us take this triangle. Let us take this triangle. So you know that this is L, this is R, and this is X. The angle is phi. Okay, so here what is cos phi? So cos phi is nothing but x by r. So from this you can write r as x by cos phi. Okay, so fine. Okay, next similarly we have here I am applying tan phi. So when I apply tan phi I am getting L by x. So from this I am writing here we can write L is equal to x tan phi. Okay, so I want the expression for dl. So here I have here only dl. So I have to have the expression with respect to dl. So what I'm going to do is I'm going to differentiate this with respect to d phi. So dl by d phi will be nothing but it is x. Differentiate this, we will be getting secant square phi. X secant square phi. So dl by d phi I am getting the value as x secant square phi. Okay, so substitute these value r and this particular value in this equations. So k lambda for dl it is nothing but x secant square phi d phi. So r square, so when you substitute r square, so bottom will be x square, the cos square phi will move upwards to the denominator, to the numerator. So here we, for secant square cos square phi, they are proportionals, they are, sorry, we can say that they are reciprocals. Okay, so we can say so that both the values will get cancelled each other. Okay, here we have 1x only get cancelled, so remaining is k lambda by x into d phi. So I have found the general expression for dE, k lambda by x d phi. So now I am going to find the net electric field in the perpendicular direction. So here I am going to find the net electric field in the perpendicular direction. Okay, so how I am going to find is nothing but I am going to integrate this perpendicular component dE cos phi. Okay, fine. So this is nothing but is equal to integration dE. We have found it as k lambda by x. So here it is cos phi d phi. Okay, so you know phi varies from theta 1 to theta 2. So let us take this as common, k lambda by x. These are constant terms. So here the integration limits, that is theta 1. Here see that this theta 1 is minus because it comes below x-axis. So it is minus. So minus, and this is as theta 2. So cos phi d phi. So when you will be getting k lambda, see whether it is visible or not. Yes, it is visible. So here we can write k lambda by x. So this term becomes, so k lambda by x. This term becomes sine phi. So this is be minus theta 1 and theta 2. Okay. We have space. Okay. Okay, fine. So this could be written as k lambda by x. So when you apply the limits, here it becomes sine theta 2 plus sine theta 1. Okay, so minus and minus will becomes plus. Okay, so it becomes sine. This is the net electric field in your perpendicular direction. Okay, in your perpendicular direction. Okay, fine. So now I'm going to find the net electric field in your parallel direction. Okay, so net electric field parallel direction. So that could be found by integrating the parallel component dE sin phi. dE sin phi. Okay, so it could be written as, so integration of k lambda by x, here it is sin phi and d phi. Okay, so k lambda by x, I'm going to integrating minus theta 1 theta 2 d phi, which is equal to, when you integrate this, we'll be getting minus cos phi, so minus theta 1 to theta 2 a lambda by x. When you substitute this, first we'll be getting minus cos theta 2, so minus of minus will be getting a plus of cos minus theta 1, so cos minus theta will becomes plus. Okay, so cos of minus theta, it is nothing but cos theta. Okay, so sorry, this is minus. Okay, minus, it becomes plus. Okay, so here we can write it as cos theta 1 minus of cos theta 2. So this is the net electric field. This is the in your parallel direction. In your parallel direction, this is the net electric field in your parallel direction, and this is your perpendicular electric fields. Okay, this is your perpendicular and this is your parallel component. Okay, so this is the way of finding the net electric field at a particular point with respect to the arrangement. Okay. Okay, so here I have given with two examples for the understanding of the distributions. Okay, so we'll see some arrangement of surface charges and volume charges after discussion of Gauss laws. Okay, so we will see that in the upcoming lectures. Okay, thank you.